these adaptive filtering methods, and we have seen one possible way for designing the update. I mean, one way. We saw only just one, okay? Which is the least mean square. So we make the least mean square adaptation. Now you know there is a different way to do it. The different way to do it is the following. You know, I can, in principle, I can always estimate or make a sample estimate of the autocorrelation, make the sample estimate of the correlation between the input and the parameter to estimate, the signal to estimate. So this is made by the matrix R and the matrix P, and then using these to estimate the filter. This can be always done. You know, the reason why we didn't do it is because we didn't want to invert the matrix R. Because every new sample, I need to make the estimate of a matrix R, the estimate of the vector B, invert the matrix R, and then the inversion of the matrix R cost. So the cost of that is approximately in the order of n cubic. So n cubic, is the cost for inverting these R to the minus 1. So this is the cost. Okay, so that one is expensive. So the cost is in the order of n cubic. Okay? That one is too much expensive. Now, rather than doing that, the real issue is, can I avoid to invert a matrix R? Now, with the LMS adaptation, we said, I don't even calculate the matrix R. I let that the computation of the inverse of the matrix will be part of my solution, but I never invert explicitly. Now, the recursively square method, which is RLS algorithm, is shaped in such a way that rather than inverting the matrix R, I update the inverse. Okay, so what does it mean? Update the inverse. So if I take, now looking here, if I take the computation of the filter A at iteration n, okay, then this is by inverting the matrix. Okay, so let's assume that this inverse has been done. It doesn't matter. We don't care who did it. Okay, so let's assume that this inverse has already been done. Now, if we say that this inverse has already been done, so if I have a new sample, I need to recalculate a new inverse. So essentially, at every new sample, the cost is n cubic. So it is n cubic plus n cubic. Okay, so I have this filter. Okay, so n cubic, n cubic, n cubic, n cubic. So it's intolerably high. Okay, so but looking with the length. Okay, so looking carefully. What is the shape of R? Where's here? And the shape of R, and if I look at Rn plus 1, is Rn plus the sum of a new data. And this comes because R, matrix Rn, is obtained by summing from k equal 1 to n, x k vector x k vector transpose, so is the outer product. Okay. Now, so actually, what I'm doing, it will be clear in a minute. What I'm doing is that, in principle, if I compute the sample correlation matrix, I should divide by n. So in principle, there should be, I should divide by n here. Now, if I compute the Pn, sorry, this is the sample, okay? So if I compute this Pn is a sum on k equal 1 to n, and then it is x, k, and the variable was theta, right? Okay, it's theta. So I'm sampling, okay? So I'm making the sample estimated this way. Now, so we can say, that in a batch way, I take the data, computing R. Then when I move a new sample, when I make a new one, so R hat n plus 1 is the sum on k equal 1 to n plus x n plus 1, x n plus 1 transpose. So since this one is what we call Rn, we can see it as an update of the matrix, of the previously computed R. Now, I told you, sorry for a minute, I told you that, I make a comment on this division by n in a minute, okay? So, now looking at this, I can write recursively, okay? P hat n plus 1. And it's sum on up to n plus x n plus 1 theta n plus 1. And again, this is P hat n. So this is exactly what is written there. Now, so, what I need to do is I need to find a way to update the inverse. Why? Because, what I need to do, I need to make from R at minus 1n to make the update. So from this one, I need to calculate R hat minus 1 to n plus 1. And, in making this update, I want to avoid the computation of the n cubic. So I want to repeat the computation again. Now, so the way to do it is to observe this update. Now this update, if I rewrite this update, this matrix R hat n plus 1 is a matrix Rn plus a matrix that contains one vector and one vector. There's column vector, row vector, but that's the same vector. Okay. Now this, this vector, so this vector time column vector, row vector. Okay. So it is a matrix plus another matrix. But this new matrix is a rank 1 matrix. Because it's a matrix composed by one column and one row, so it's an inner product, okay? Outer product, okay? So, because of that, I need to see if some on the algebra made the following computation. And the computation is the following. So, compute, so update, not just the direct matrix, but the inverse. Now, if I look on that, there is someone that computed exactly this update. The formula that we are using is the so-called Woodbury identity formula. Woodbury identity says the following. Okay? So, you see this interplay between mathematician and a statistical method, our statistical method. Okay? So it's that we use the mathematician. So we use the mathematical derivation. So we go search and we call our, algebraic friend, and he says, obvious. If you have a matrix A, okay, and you already have the inverse for that. So assume that you have a matrix A, and you update the matrix with the new matrix B transpose, and you want to compute the inverse for that. Okay. This is equal to the inverse of the matrix plus a something. This is plus something is because I'm speaking too far away. Okay? So anyway, plus a something. Okay? Now, That means that you know, but this one is exactly what we are looking for. Because this A is taken by the role of this hard hat, and this is taken by, so this rank 1 matrix is taken by the role of this outer product. So overall, you know, let's see if the Woodbury formula makes our, you know, makes it's useful for us. Now, if we go to see the Woodbury formula and we implement on that, we see that the inverse, okay, can be updated in this way. I thought it was a laser point. So, you know, it can be updated in that way. So, the inverse is the inverse in the previous iteration, which already computed, plus or minus, you know, the updated. But you see, in the update, I have always the inverse, which already computed, the inverse, which already computed, and the inverse. So, you know, I'm not recomputing the inverse, because I computed the previous iteration. So this one, you know, I have r hat minus 1 multiplied by xn. Okay? So, you know, if I compute first this, and this is a matrix time vector. So this one involves the n square multiplication. So I have n square multiplication, then, you know, then this one is creating, a vector. Then I have another n square multiplication, but you know, this n square multiplication is the same as the previous one, so I'm not recomputing. So overall, you know, this implies a number of operations which is proportional to n squared. So since this one is proportional to n squared, it costs less than n cubic. Okay? So that's the way to implement. So now, if I take this computation of the inverse, let me say, it's not a computation of the inverse, is that I am taking the inverse computed in the previous iteration, and then I'm updating to the new iteration. And this new iteration means a new batch of data. So, you know, I have this sample and I'm updating with new one. Okay? So now, you know, I mean, when I manipulate my formula there, and I get the updating formula for the recursive least square algorithm. The updating formula, you know, is by recomputing that. Okay, so this one is the inverse. That is the error. I mean, everything goes inside. Blah blah blah. So you know, this has been, you know, is a term. So this is not computed by computing the inverse. And this is the new data. So the update of the filter is obtained by the filter in the previous iteration, plus again multiplied by the so-called error. Now, so this is the new update formula. So, you know, it's more expensive because in the previous one, the cost of the update in the least square, in the LMS, is only in the order of n multiplication per iteration. Here the cost is n squared. Okay? So it's more expensive. So RLS is more expensive than LMS. Okay? So let me now, you know, put into a sort of table. I will make it after discussing about the n coefficient. So, but you know, I'm going to put into a table what is the difference between LMS and RLS. Okay? Now, before making step forward, let me dissipate the issue about the scaling factor of 1 over n. Now, so you might argue that this is not the sample correlation, because in order to have the sample correlation, this should be divided by n, this one, okay? Now, you know, but you know, if this one should be divided by n, this one should be divided by n, right? But if I take the estimated value A, you know, of the filter at the n iteration using that, this is equal to r hat minus 1 n times p at n. Now, what's happened? It happens that this one contains 1 over n, and this one contains a multiplication by n. So the scaling n simplifies between the second term and the first term. So for the sake of the filtering, this n scaling is not necessary because it simplifies. Okay? So it goes away. Okay? Clear? Sleepy? Okay, thanks. So, now, so this dissipates, the issue about having the scaling factor. So I call it a correlation, I call it a cross correlation anyway, even if there is no scaling factor, because for the sake of computing the filtering, any scaling factor, okay, which appears here and there is simplified, because I have r to the minus 1. Okay, I have r to the minus 1. So if I have 1 over n and n here, okay, that means that this term contains 1 over n, and this term contains 1 over n to the minus 1, which means n. This and that simplifies. Is clear? Okay? Now, see the record, Okay, later. So anyway, so let me, move to the point where I want to show you what is the major now, in comparison, what is the major difference. Now, so LMS update and RLS update. So in the LMS update, a hat n plus 1 was equal to a hat n plus mu, that we need to choose it, error at iteration n, time x, n plus 1. Oh, we are on filter n. Okay. That's what we show previously. Now the new filter is a n is equal n plus 1. N plus 1 is equal to a n plus, I have the inverse the new data, and then I have the error. Now if I compare this to that, I can see that, the update formula is the same, except that, I'm replacing the mu factor with the r. And so, for this reason, intuitively, it's like to have, a different gain with respect to different direction. On the other hand, here we have the same gain for all the direction, for all the gradient direction. Now, computation complexity. The update here, it costs one multiplication for every coefficient, so the cost is m in the order of n. Now, the cost here is in the order of the update of the Woodbury formula, which is on the top there. So the cost is n squared. Now, time for convergence. The time for convergence is proportional, approximately, to lambda max on lambda min, in the best case. Okay? So essentially, the slowest one, so if I have a one eigenvalue close to 0, is a disaster. It never converges. Keeps going, keeps going, keeps going, never converge. This is for the elements. Okay? So, this is the dependency. Now we need to see here. Okay, so now there is some, some aspect, okay, related to which data is computed. So, for instance, I'm using the new filter is using the past data, okay, and the data at the time iteration and plus one. Now, like here, you know, if I look at here, this is a theta hat, theta minus theta hat. But you know, this theta hat is obtained by taking the filter at the previous iteration and with the data at the new iteration. So there is a one sample mismatch. You see here also from the formula for the comparison. There is a one sample mismatch between, you know, the update formula on the LMS and the update formula on the RLS. Okay. Now, in order to highlight the fact that there is a one sample mismatch, this error is the error on iteration n plus 1 when using the filter calculated iteration n. Sometimes, you know, I indicate it as epsilon n plus 1 slash, I mean, you know, with the bar n. This filter, this means that this is the error, you know, at the sample position n plus 1 by using the filter computed up to the iteration n. Okay. Now, another way, you know, which is unfortunately, you know, since I moved this part before, we cannot really appreciate, but you know, I can also group, so I can group the terms in a different way, like here and there. So, you know, then grouping this way, I can see that the update at iteration n plus 1 is equal to the filter, the iteration n, or the sample n, plus g. So if I call this term as a vector g, now this gn is called filter gain, and so, or update gain. Okay, so, you know, I can group, you know, the RLS update formula as, you know, the filter coefficients, the previous iteration, plus a gain multiplied by the error. Okay, that's another way to see the same formula. Now, the reason to look at this representation is because this is exactly the similar structure of the filter as for Kalman filter. That is something that we will see. So, anyway, yeah, this is, you know, how to compute the update. Okay. Okay, this one is highlighting that, you know, this is taking the same role as having, you know, a matrix type, new factor as for the LMS. Now let's see the convergence. Now, for making the convergence analysis, we make the convergence by considering the identification problem, which is right here. So the identification problem, just to recall you, that I have X and entering into a filter A0, and I have some noise superimposed, and this is data N, and then I'm taking a parallel filter, which is inputting with the same X. I have AN, which is a varying filter that, you know, is varying because I am adapting. I'm estimating as output for that is theta hat, and then, you know, I'm taking these as the error. Now in errorless, so in recursively square, I'm taking, you know, this error by taking the filter and the input on the new iteration. Anyway. So let's see about the convergence analysis. So in convergence analysis, I want to see how fast this one is going to that. Now, so the preliminary operation I need to do is that first of all, I need to consider that when I make the update of the inverse of a covariance matrix or correlation matrix, that's what I mean, correlation matrix, I need to initialize this inversion. So that means that, you know, since I update, since the key idea of RLS is that I update Rn plus 1 is computed from Rn minus 1n plus or minus in a correction term. Since I'm computing this way, so, you know, I need to decide how to initialize that. So I need to initialize the RLS by setting a certain value for R0 to the minus 1. So that is the initialization. Okay. Because I need to initialize. Now, you know, I can make some remarks on that before considering convergence analysis. You know, how to initialize that? I mean, you need to initialize in such a way that you can always compute the inverse of these R0. So, you know, if you initialize with R0 equals 0, you cannot compute the inverse. So that is not a good initialization. So a typical initialization is that you initialize by R0 equal to a small number time identity. Because in this way, R0 to the minus 1 is equal, you know, is identity divided by the scalar delta. Okay? That's, you know, that's a typical initialization. So you can initialize in this way. So that means that since I initialize with the delta, you know, delta is not a connected delta, it's just a small number, okay? So since I initialize in this way, I mean, the convergence is reached when this initialization is forgotten. Because this initial condition is wrong, is mismatched with respect to the true solution. So it's like, you know, imagine that, I'm initializing an algorithm that has to, I don't know, you initialize a robot that has to go in that direction, okay? But, you know, I mean, when you put the robot, you need to put the robot in some direction. So you randomly choose where to put. Now, how long does it take to reach the convergence? Which means, how long does it take the hypothetical robot to start and looking around, and, you know, after a while, finding the right track? Okay? So, since we initialize wrongly with respect to the problem, how long does it take, for instance, in the specific setting to forget the initial condition? So there is a transition time which was not existing here. Okay? So there is a transition time which is necessary to forget the initialization. Okay? Now, because of that, you know, we need to revisit, okay, our update. And so in our update, we need to keep in mind that at the end set of data, we have our correlation matrix plus the update. Because this is how I update it. Now the reason to put the update, now there are some technicalities. The reason to put the update R0 different from 0 is because I want to start having something. I want to start having an output before having a full rank matrix R. Now, why full rank? Because I'm computing the inverse. Don't forget, I'm computing the inverse of a matrix. And I need to have a matrix to have a full rank before computing the inverse itself. So since I need to compute an inverse, I need to have a full rank matrix R. So I have two ways. One possibility is that so about the RLS initialization. So one possibility is that I start with R0 arbitrary, okay? Then, you know, if R0 is arbitrary, then I mean, I start to have an estimate of the filter from n larger or equal 0. Okay? I start having something. The other way is, you know, I start with the initialization R0 equals 0, which means I'm setting R0 equals 0. So since I set this one, and since I need to compute the inverse, the only possibility to compute the inverse is that this inverse can be computed only if Rn is full rank. And you know, and how do I have a full rank? Now, remember, so Rn is the sum of matrices, so similar to that. Look at here, similar to this. So it's outer product of rank 1 matrix. So I have rank 1 matrix, so the rank is 1. Plus another rank 1 matrix, rank is 2. Plus another rank 1 matrix, rank 3. Blah, 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 and so on, until I reach n. So when I have n samples, this sum of terms is a rank n matrix, then I can start to compute the inverse. So that means that, you know, I need to have a at n when n is larger or equal than the size of the matrix. So in other words, I mean, the first capital N steps are only devoted to create the matrix R, capital R, and after n samples, you compute the first inverse. After n samples, okay? So you initialize, and then, you know, after n samples, you compute the first. And then you have the algorithm, keep the algorithm running. Okay? So that's the second option. So you can initialize, so it's like to have a robot, you know. I mean, so we have a robot, and the robot has to go there. Or it's, you know, you need to go somewhere, okay? So suppose that you need to go to the center, to the Duomo Milano, you know, and you are coming from another city, and you drop here from the event, okay? And you're here, and you open your eyes and say, okay, I need to go to the Duomo now. So option 1, I start moving. I mean, something happened, okay? So after a while, you know, I ask, I do blah, 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 and then, you know, after a while, I go straight to the Duomo, okay, to the center of Milan, okay? Which is usually the option, I mean, the way of how the engineers do, you know, they keep moving. It's like when you use the computer, you know, you use a new program, you never read the manual, you know, you start moving your hand, right? Okay, so the other option is, you know, you don't move, you want to have all the variable, you want to know everything, you read the manual, okay? You have a new software, you read the manual for 3 days, and then you close the manual and you start moving, you see? Okay, that's the second way. So these are the two different ways. So the first one, you start, and you hope that after some time, you keep moving in the right direction, number 1. Number 2 is that you don't move, you don't do anything, until you don't have a full rank matrix capital R, which is a correlation matrix. Once you have the full rank matrix, you compute the inverse, and then you start the update of the inverse of the matrix. Okay, that's the second one. So, you know, it depends on the case. So if it is important for your software, your problem, your algorithm, to start having something, you're better to initialize the first one. If your application, it's better to avoid any error, any mistake, you know, every data can be religiously taken. And then, you know, since is taken as a truth, then you're better to wait a little bit. Then you use the initialization of the truth. Okay? So, now this has impact. So the convergence analysis now is that I need to forget the initialization. So you know, the convergence is how long does it take to forget the initialization. So this is written by the formula, okay? So, you know, I mean, what we said in words can be said by the formula. So let me help you to read this formula. So what I do is, first of all, I'm taking, you know, that's the problem. So my goal is to estimate that data is 0, and you know what I know is that for the number of iterations going to infinity, this is going to that. Okay? Up to the noise. So now you know what I make. I define the estimate of the correlation matrix, and up to so with n iteration, and this is for k going from 1 to n plus R0, which is the initial condition. Okay. Then similarly, I have the cross correlation, okay, which is xk and theta k. But you know, theta is obtained by that. So I mean, it's convenient to plug for the analysis, not for anything else. So for the analysis, when I plug this into that, I mean, I isolate theta 0 into the Pn. Then, you know, if I recall what is Rn, and that is equal to this one, okay? So in order to go from here to there, I'm using the identity that comes from here. So putting all together, which means putting the first and the second all together, what I got is An, okay, so you know the estimate of the adaptive filter at iteration n is equal to A0, which is a true one, okay, minus blah 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 A0 plus blah 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 W. Okay, so let's see. This one, you know, depends on R0. So this term depends on the initialization. The second term depends on the noise. Okay? So, you know, this one depends on the initialization. And that one depends on the stochastic part, which is on the noise. Now, what is the convergence? So let's set the condition for convergence. What is the convergence in mean? So we know the story. When you say convergence in mean, we apply the expectation here, and you know the expectation goes all the way there. Now, when we apply the expectation here, you know we replace the estimate of the autocorrelation with a true value. And so, you know, I mean, this estimate now should contain the scaling factor n, because in the way we define, this Rn does not contain the scaling factor n. So once we plug in the scaling factor n, we got that. So this is the next step. So, you know, I have the expectation which is only acting on that term because the noise is 0 mean, so you know the expectation to the noise goes to 0. Okay, there is no expectation. So, you know, what we notice that in the mean it's equal to A0 minus blah blah blah. So this blah 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 term, okay, so this additional term is the bias. So the RLS solution is biased, and it's biased by the initial condition, which makes sense. When I, you know, since I want to start immediately at the beginning, my solution is wrong. So, you know, what I need to, I hope that after a very long number of iterations, this term disappears. Now, as I told you, you know, a very common way is to initialize as a diagonal matrix. Okay? The reason why for diagonal is because it can be inverted trivially. So if I initialize in this and this way, then my bias is a delta number which is hopefully small divided by n time r to the minus 1. So you know, if n is large enough, then this term disappears. So the RLS is bias, but asymptotically for n going to infinity is unbiased. So for a small number of samples is biased. This is what we expect. So that means that it's something that we didn't have on LMS. So we have a bias. But you know, luckily it's going to 0 with n. Okay. So if you know we can count on 100 samples, or enough large, n is large enough, then you know this is going to 0. By the way, delta is helping me. So if I choose delta, the scaling factor very small. If I choose delta equal 10 to the minus 3, then you know this is disappearing very quickly. Okay. So now the other way is the convergence in the mean square. Now for the convergence in the mean square, what I need to do, I need to write the difference between an and minus a0. You know, since an is this, so the difference is, it's very simple to be computed. Now let's avoid here. There is another assumption. So we avoid the bias. Now we avoid the bias because n is large and r0 is delta, or you know, n is larger or equal to n, and I initialize, I weight n samples to start the filter. So it depends on the different cases. So you know, regardless for that, I can assume that the bias is negligible. Now, if I assume that the bias is negligible, then the convergence in the mean square depends only on the noise term, which is that. So now, you know, I compute the expectation for that. I manipulate everything that goes here, and let's see the next step. Blah blah blah. You don't need to read it. So, and so it comes out, so it comes out that the convergence in the mean square depends, blah blah blah, depends on the sum of the inverse of the eigenvalues of the correlation matrix R. So, you know, it's not similar as the mean square is not similar as the LMS. The good news is that regardless of this dependency, is going with n. So you know, the more n grows, the less this one is dominating. And you know, and for n going to infinite, this is going to 0. Fast or slow, depending on the eigenvalue of the matrix R. It's different from the LMS, because LMS, you know, asymptotically has a mean square error which is different from 0. So let's add an additional item to our plot. So now this one is the initialization, so at convergence, so let me say now at convergence we have a mean square error plus excess. Now that one at convergence, mean square error is going to 0, which means that on the mean square, okay, an is going to a0. not only the mean, but also the mean square, which means there is no dispersion. It's different from the other. There is still some jittering on the parameter. So, good, bad. But this cost n squared, this cost n. So nothing comes from free, because that one is more expensive. So you know, I mean, if you imagine that n is, I don't know, imagine that n is 50. In one case, the cost is, you know, is 50. You know, so the cost of LMS is 50, and the cost of RLS is 50 squared. Okay? So, you know, 50 squared means that this one is 50 times lower than that. Because 50 squared is 50 times 50. Okay? So, if this one takes 1 second, this one takes 50 seconds. If this one takes 1 microsecond, this one takes 50 microseconds. Okay? So, you know, that's just to give you a number. Okay? So, cost. Now, about the learning curve. Okay?
Professor, sorry, I have a question in the previous page. It says that it says that we can delay n so that it is unbiased. But
Yeah.
we have to initialize and then
No,
wait
you
for
don't
n.
initialize. You know, you have your data. You have your experiment, okay? And you know, and your filter is long n samples.
Mhm.
So this is lower case, okay? Now my filter is that one. Now, if I initialize, I start having results. Okay? So, you know, if I initialize, I take these samples and I make an output.
Mhm.
Then I slide here and I get an output. Then I start here and I get an output, and so forth. Okay? So this is the case. Of course, this one is capital N. Okay. So my output is, of course, is shifted by capital N
Mhm.
because I mean I need to take n samples to filter. Okay. So this is what's happened. Okay. If I initialize R0. Okay.
Mhm.
Now let's
And
see
this
if
is
I.
biased.
Yeah?
This is biased.
This is biased.
Uh-huh.
Okay, yes. Let me write the difference. This is biased. Okay? Now, let's assume that I do differently. Okay? I don't initialize. Now, if I don't initialize, I use the same time axis. Okay? So if I don't initialize, what's happened is, you know, if I take the first block of data, okay, when I take this block of data, then I start putting this block of data into the matrix R. Okay? So from here, I get, let me write it here, I get R1, which is X1, X1 transpose. Okay? But you know, this one is rank 1. And then I cannot invert.
Mhm.
Okay? Then you know what I do is, I make a second one. And I take this group of data. Remember, this is X1. So this one that I highlight is S1. Okay? Now, let's make X2. X2 is this one. So, okay? Because I lose one sample and I have a new sample.
Mhm.
Okay? Now, from these X2, then I get R2. So R2 is equal to X1, X1 transpose plus x2 transpose. Okay. But you know, this one is rank 2. Actually, you know, if the sequence is the same, it might be rank 1. But you know, let's avoid the pathological case, okay? Because you know, if the set of data are exactly the same, you know, that the second block is a rank 1. And so summing is still rank 1. But you know, let's avoid these pathological cases. So these are 2 is rank 2. You know, let's suppose that capital N is equal to 10. So you know, I mean, that one is rank 2 and I cannot invert. I cannot calculate R2 to the minus 1. Okay, so I take another block. Which means that this block is by taking this set of data. Okay. Then from here I compute R3, which is equal to R2 plus X3 transpose. Okay. Now this one is rank 3. I cannot compute the inverse. So I keep going until when? Until I don't get, okay, you know, this set of data, okay, and this set of data is Rn. Now, if I have Rn, okay, then I have the sum of k equal 1 to capital N of x, k, transpose. Okay. Now, this one, since I sum n vector, okay, this one is a rank n. But since the matrix is n time n, okay, now is full rank. Full rank means all the eigenvalues are different from 0. Excellent. Now I can start inverting. Okay? So here at this stage, I can start here now. I can compute this one here. R10 and to the minus 1 because it's full rank. Okay? Now I have the algorithm starting. So where do I get my first output? My first output is not here as before. Is here.
That's the delay.
That's the delay.
Oh, okay.
Is it clear?
Yes.
Okay. I mean, it's these are stupid concepts. You know, if you try yourself, you know, it's very trivial. Okay. So you get a delay by n. Now, of course, I mean, the sample correlation by n samples are not a good correlation. It's because, I mean, you don't have enough samples to calculate the sample correlation matrix. But you know, it's better than nothing, okay? It's better than nothing. So it's, I mean, it's advisable, so I would advise to start having a good autocorrelation, to have a number of samples that are at least 2 times the size of the vector, okay? Just to have that. So that means that you start having, so you compute R hat, and you have the filter start, let me say, working. Okay? So you have a, you have a delay by n samples, which in this case I choose 10. Okay? Now, but you know, to have a very good autocorrelation matrix, so if you decide this second choice, you know, if you want to have a good autocorrelation, you're better to still delay a little bit before applying the filter. Because the autocorrelation that you compute here is full rank, but it's not good. How can I say? It's so after 10 samples, it is full rank. So which means it fulfills the condition to make it the inverse, but it's not reliable enough to make the output of the filter to be reliable itself. So this is the reason why for that one, it's a recommended. Let me see if I have a space. So you can, it's suggested. Let me write the suggested with these green. To weight the 2n samples. So you weight another n such that your autocorrelation matching is well confident. Okay?
This could be a learning curve?
Yes.
It doesn't.
Yeah, this is the learning stage. So you make it the learning stage, right? You like the use of learning language. Okay. So you make the learning. Yeah, right. You are right. It's me that it seems so obvious. Okay. So you are making this learning stage longer to have a reliable output, and then you start computing this output. Okay, that's exactly the case. So for the RS, you can start immediately. Okay, number one, or you can start after n samples, but you have the invertibility of the matrix R, but not the reliability of the autocorrelation matrix. Or you can make this learning stage, okay, longer in order to have invertible matrix and reliable matrix R. Because remember, everything depends on R. Depends on P and R. But the R is less controlled, because when you have a matrix and you need to compute the inverse, you don't know exactly where each term goes. Because in computation of the inverse, you have too much, it's so complicated to see some uncertainty, some terms, where it's going when you compute the inverse. And so for this reason, it's better to stabilize the computation of R and then you invert. Okay, that's another way. So making the parallelism of having a new phone or having a new computer, a new software. In the first case, you start touching. Okay, you see after a certain iteration, you get something. Okay, that's the first one. So in the second case, you wait, you read all the pages, and you say, okay, it's reasonable. Then you start working. Okay, and the third one, you read all the pages twice. So in the first one, you read it. You learn it with, okay, so wait a minute, read again some parts. So you make another n samples, and then you start. Of course, the third one is more reliable. The third case, you took a learning curve, learning time interval longer, but it's in some application you cannot wait that long. Okay. In some application you need to start outputting the data, because the data are floating, and if there is an anomalous condition, perhaps you can immediately see at the beginning. Then it depends on the case. Okay.
But in this way, we avoid the excess mean square error with the RLS in this way, right?
Yeah. We don't have the excess mean square error. You have no jitter on the parameter. Okay. And you have no jitter on the parameter. Also, you have no excess mean square error. We'll see in 1 second.
Professor, can I say something? In the first part, the system is more sensitive to any perturbation that happens between two samples. But in the second case, the system, since it's rely on the xn+1 in the updating process, so if any perturbation happens on real-time case, the updates are sensitive, and system 2 looks more robust. And in the terms of transfer function, since these two are integral action, the first one is 1 over z plus 1 and the other one is z over z plus 1. So the first one is less robust compared to the second one.
But you are neglecting the matrix, this matrix, you are neglecting that. everything you're saying makes sense. If you neglected the presence of this term. So we're talking about the adaptation of that, it's not the filtering in the robustness of the update. Let me say it in a different way. Okay? Here, it's like to have a group of people, and we need to go to the bottom of the valley. Okay? We are minimizing here and there. Okay? It's a minimization. In the second case, it's hidden, but it's a minimization anyway. So we have this valley, we need to go down. Okay? Now, in this case, we go down, but we say that everybody is making the same step. So a good skier, which can go easily, make a long step, can go down to the bottom of the valley, and a bad skier, which is trembling on the ski, they need to make the same step to left, okay? Which makes no sense if you think about it, because the good skier, you can let him go, go, and then I can come with my speed, So in this way, in the first case, the slowest is lowering all the others because the slowest is making the step small because the slowest is refraining, is like breaking all the others. That's the first case. In the second case, because of the presence of this, what I'm doing is I'm giving a different speed to different skier, but this speed is computed the previous iteration. Okay, because so at the n plus 1, which is now, I'm computing the speed from the computation that I collect all the, if you want to say, all the learning that I did for all the correlation property coming from the past to make, these cooperative and collective ski, and the one that is fast is going, the one that is slow is, is going slow, but it's different step. Here the step is the same, and is ruled by the slowest one.
But you're affecting xn plus 1 here, but there you're affecting xn. So if any perturbation happens in this case, we have it for the updating rule. But there we don't have it.
Here I'm updating with my past, right? So
but
I'm
here,
making my update on my past data for the future one.
yes, but here you're affecting the current xn plus 1, so it's more robust. That's what it is. Yeah.
I don't know. You
Okay.
might be right. Yeah, you already told me. You might be right, but I don't know. I don't see immediately.
Okay.
You need to.
I have the math.
Okay. You clarify your mind, since the last time. Very good. Now, so about the learning curve, which is another parameter which is relevant, okay? About the learning curve for RLS. So the learning curve for RLS, is by manipulating, and so it's coming from which is I calculated before. So it's coming from the dispersion, from the jittering of the parameter. But in the previous case, the jittering of the parameter is creating the excess mean square error. But here we don't have the jittering of the parameter. So asymptotically, I don't have any jittering parameter. This is what I expect. So this reflects in the learning curve. So the learning curve now, this is what to remember. So the learning curve for the RLS is J mean, which is the minimum one, plus capital N divided by N of the iteration multiplied by J mean. So essentially, what's happened? It happens that in a previous case, this was the excess mean square error, which does not exist here. So we have no excess mean square error because we have no trembling of the parameter. Now, if we want to declare, how many speeds is it converging? Now, the number of speeds is enough that this second term is much smaller than the first one. So, what does it mean much smaller? Now for the engineering side, it's enough that n is equal to 2 times capital N, which means that the second term here is J min 1 plus, so it is N and capital 2 times capital N, and so this means that it's 1/2. So it's enough that N is larger than 2 times capital N, that this one is negligible because it's smaller than 1/2. So it's 1 plus 0.5, okay? So which starts to be negligible. So these sets approximately the number of iterations to reach the convergence, which is N equal to capital N. Number of iterations equal to 2 times the length of the filter. So now, if you remember the previous case, we said already that the filter is taking 2 times capital N a number of samples to train properly. Now, this proper training is not only because of I need to compute properly the correlation matrix, but comes also from the learning curve, because the learning curve contains a second term, and this second term, that was the excess mi square, which is not existing here, is negligible. And so we have a convergence time. So now, going here, which is the time for convergence? Now the time for convergence here is approximately 2 times N. So convergence, we have at convergence we have the excess mi square error, and here we have no excess mi square error. Here the parameters are trembling, here they are not trembling. When you reach the bottom here, you keep moving, here you are not. Now you need to tell me that I am telling something wrong here. Okay, it seems perfect, okay? So let's summarize. Yes, it seems perfect, okay? But it is not. I'm faking you, and now you need to tell me why. Let's remove that. There is a mistake here. What is a mistake? Why is it trembling? Remember, the excess mi square error depends on mu. Okay? So if I keep a mu high, then I'm ready to react. If I keep a mu small, then the excess mi square error can reduce. I can shape. You were telling me, the possibility to shape the mu such that when I'm close to convergence, I take the mu and reduce the mu. Okay, which is called gear shifting, So I reduce the mu. Perfect. But there is a mistake of all that. And especially what I told you. And I'm just giving you the hint. The mistake about that is that this method now is converging to the optimal solution in a stationary condition. Why? Because in this method, I'm computing, remember, I'm computing R at N, which is summing x, k transpose. So it is summing n vectors with the same importance. So if this algorithm wants to react to a non-stationarity, it has no possibility to react. So this one is too hard to react. It's almost impossible to react to this algorithm. So what I said is, all I said here is optimal for a stationary condition. But you know, I mean, we need to remove these, you know, these rigid constraint on the stationarity. And this rigid constraint on the stationarity can be removed by making the computation of this part to contain a memory. So what I'm saying, you know, is this. If I make the RLS in the way that I just told you, okay, if I have a signal that is behaving this way, no stationary, pom, another non-stationary, pom, another non-stationary, okay? Now, this is the data, okay? So, no, it's a non-stationary, non-stationary, non-stationary. I don't know, it's a tree, earthquake, or whatever, okay? Now, what's happened with this? With this one, you know, start filtering. No stationarity, try to adapt. Okay, try to follow, okay? They know I'm slow and fast, you know. If I'm lucky, my eigenvalue difference between, you know, lambda max, lambda min is small, then I reach, okay, the convergence, okay? Then I'm there, bam, a new no stationarity, change. So this one is always ready to react. So you pay this ready to react by the fact that you have an excess of b-square error. And the excess b-square error is due to the fact that, you know, since you are always ready to react, you react also to the realization of the noise. And then you update with the single sample. Now, about that one, what's happened with that? In the way I did, you know, I mean, I'm summing. So if I have a non-stationarity, you know, I have no way to recognize that it's no stationary because it goes into the sum. So when I'm here, I'm not reacting on the new data. I am simply averaging all because you see I'm summing all the data on the past. So, you know, but the data that happens 3 years ago, okay, imagine you have a song. So if you have a filter, imagine you have your own adaptive filter. And you have this adaptive filter which is applied to the, you know, the active noise cancelling headset. And so your headset is still remembering the song that you played last year. Makes no sense, right? Because it has an infinite memory. It has a memory that, you know, remembers everything because it keeps summing. Keeps summing and computing. Keeps summing and computing. No way. So the way to avoid that is to make the RLS that we computed. So we establish, you know, what is the property of RLS. So we need to make it reactive to the non-stationary phenomenon. And this is carried out by the exponential way. So we need to introduce a forgetting factor in the algorithm. Now, so the forgetting factor is that lambda. So you see there. Is lambda. So that lambda is acting as a forgetting factor. That lambda is smaller or equal than 1. So what's happened on that? I mean, the past is counting lambda time. Now, if lambda is equal to 1, so I have a memory that is infinite. But if lambda is smaller than 1, I have a finite memory. So this means that if I'm acting on this sample, the past is weighted by an exponential weight function, which is behaving approximately this way. Now, the exponential weighting function, which is the memory, depends on lambda. So if lambda is very big, then you know my memory is very large. If lambda is very small, then my memory is very fast. So I have a lambda to the power of k memory that is keeping memory on the past sample. And you know, if lambda is equal to 1, I have an infinite memory. This is lambda equal to 1. So the past count as if it was present. If I make lambda very small, the very far past counts 0. It goes away, it fades away. So the past fades and the present is important. So if I make it this way, then my algorithm, my RLS becomes adaptive. Becomes adaptive in the sense that it becomes ready to adapt to the non-stationary. And you must use this. So you will realize in the workshop next week that you must use RLS with memory if you want to capture the signal hidden in the noise. If you don't apply the RLS with memory, you never capture the signal hidden in noise. Then you will see next week that if you apply the LMS, you converge, but it takes more time. So you will see that, since next week you will filter, you have the headset, you listen to music, you listen noise, music and noise, and then if you apply the LMS, it's a slow conversion. So you start to listen music and noise, clean, then after a while you listen to music very nice. Okay, but this one depends on how you initialize. But you quickly get the clean music. Okay, you quickly get the clean music. But remember, if you don't get the clean music, or you get the clean music at the beginning, that after some time starts degrading, means that you shaped your RLS very nicely for the first part, but you need to introduce a forgetting factor because the filter is changing. You need to change it. So if with RLS you get a very nice song at the beginning, which means it's faster than that, but then after a while it starts getting noisy, that means that you need to introduce a forgetting factor into the filter, because you need to forget the past. Now, there is not much to say rather than the way it is, the single equation are modified. So, you modify the single equation this way, that's a lambda. In the conventional way, if you put lambda equal 1, you got exactly the previous argument. Exactly that. So, and we can redefine the convergence in the mean. So let me skip it, but we can redefine the convergence in the mean, the convergence in the mean square. We can define, how many iterations takes to converge, blah, blah, blah. But essentially, you see, this is the learning curve. The learning curve can be rewritten. You remember, the learning curve depends on capital N divided by n. Now I have a new n. This is an equivalent n. This equivalent n, which is here, depends on the ratio of lambda. So, and this is establishing the number of steps for convergence. Okay, and so that's and that's all for that. Now comparing. So just to compare. So now, making a precise computation of how many multiplication you need to spend for LMS and RLS. So if you want to make it very precise, we can notice that the cost of multiplication per iteration of LMS, N stands for normalized, which means I use a normalization factor. Okay. LMS costs 2n. Okay, 2n is due to the fact that I need to multiply by epsilon, and RS cost, as I said, n squared. If I look at carefully, it's not n squared, it's n multiplied by n plus 2. It's n squared. So here is the cost is n versus n squared, approx. Now the time for convergence of in number of iterations. Now, we remember that the convergence in the mean is the ratio between lambda max and lambda mean. But the convergence in the mean square is n times more. You remember? It's n times bigger. Okay? Just a rough computation. So that the convergence is n time the ratio between the eigenvalues. So it depends on the random process you are manipulating. In case of RLS, the convergence is approximately 2n iterations, 2n samples. So it's faster. And you will see it's clearly very, very much faster. And now another parameter which is nice to consider is, now this is technical, so let me show you. You know, imagine that you have your data, okay? Okay, now, you know, in the first case, the number of iterations to converge, in the first case means LMS, is the number of iterations is n times lambda max lambda min. Now, that means that, I'm using, so it takes a certain number of iterations to converge, okay? Now, so assume that I converge here. Here is n times lambda max to lambda min. Okay, so I've done this much iteration. But you know, every time I make an iteration, I'm computing, so I'm making n multiplication. So that means I'm making n multiplication, n lambda max and lambda min times. So how many, so what is the cost for LMS in total to reach the convergence? Now the cost is the cost of one iteration multiplied by the number of iterations. So since the cost per iteration is n, 2n, n, so it is 2 times n, which is the cost for one iteration, times, you know, the number of iterations to reach the convergence. Okay, which makes 2 times n squared, and then we reach lambda max lambda. That's for LMS. So you know, if the time for convergence is fine for you, if that you take such an amount of samples to convert, then you want to see, how much it costs to be. Because you remember, assume that you want to have a convergence, you throw away all this data. Because you use it. You will see next Wednesday, you know. When you are there, you are listening to music, you see the music with the noise. And you know, since you listen to music with the noise, you are there, you say, okay, you know, I'm still waiting. So how many multiplications should I take until I start listening to music, okay? This is the third computation. So the cost up to the convergence is 2 times n squared, and then the ratio of the eigenvalues. On the second part, you know, since every step costs n squared, since I converge into n samples, so the total cost up to the conversion is 2 times n cubic. Now this 2 times n cubic is dispersed in 2n samples. So, in other words, looking right and left, what I notice is that the LMS, you know, is excellent in case lambda max to lambda min is close to 1. So when, you know, the sequence or the data has a correlation matrix which have the eigenvalues that are not spread, then the LMS is not there. And the cost of the LMS to reach the convergence is better than RLS. At the same time, the LMS is fast converging, which is excellent. Now, if on the other end, lambda max to lambda min is big, which means you have a signal with a random process with a big spread on power spectral density. Because remember, lambda max and lambda min, the ratio depends on the property of the power spectral density of the random process. So if you have a random process which has zeros or similar, then the LMS never converge. So we will see that, you know, some part of the LMS never convert. You're there, and you can still see that, you know, it's improving, like in the music. You know, next week it's improving, but it never does it. Okay. On the other hand, on the right hand side, you know, you converge, and the number of iterations to converge is 2n. So, you know, it's that one. Now, one word for the wireless. Okay. In wireless, typically is used the RLS. The reason why it's used the RLS is because you can imagine that those samples are the samples that you are using to estimate the time varying channel, communication link, which is represented by a filter. Now, you want to be sure that it's converging within a certain amount of time, no matter what is the filter, no matter how the filter, you know, the process is white or not white. You want to be sure that it's converging in that case. So this is specifically when you are transmitting wireless. When you're transmitting wireless, you are estimating the channel by using a certain number of known pilots, known symbols. You want that within those known symbols, the estimator converges no matter what is the environment where you are applying. Because you want to keep that set of data, that length, to be fixed independently of the application, independently of the context where you go. You need to say that you can use your mobile phone here, there, and the algorithm converge. Okay? So the RLS is convenient in any setting where you want to be sure that the algorithm is converging in a certain number of samples. You want to be sure that, for instance, the learning part is bounded to a certain number of samples. You want to be sure that 2n samples are enough to complete the learning stage. And, you know, and that's the case. More than that, it depends on the application. Okay. So, by the way, next week, Monday and Tuesday, there is a workshop by Huawei. Have you seen it?
Yes.
Okay. I don't know about, what is, are you recording this?